Hi everyone, this is the first of 3 videos that covers igneous rocks. And igneous rocks are simply any rock that forms from a once molten state. In other words, if we have hot liquid rock material called magma, if it's deep underground, or lava, if it actually erupts at or very near the Earth's surface. Okay, so igneous rocks just represent cooled magma or lava. A useful way to think of igneous rocks is to distinguish what are called different igneous textures. And in this case, a texture in the context of igneous rocks, it doesn't mean whether the rock is rough or smooth. It refers to the components of the rock. And in this case, we'll describe 3 main rock components, including crystals, glass, and pyroclastic fragments. Crystals are just minerals that are forming in the lava or the magma as a result of cooling. Glass forms in volcanic rocks where the rock either crystallizes poorly or it cools too rapidly for crystals to form. So you can think of volcanic glass as non-crystalline material. And then finally, pyroclastic rocks contain rock fragments that have been blown explosively out of the throat of a volcano. So without exception, rocks with a pyroclastic texture are indicative of explosive volcanism. So here's a slide to kind of summarize what happens during the cooling and crystallization process in a magma, a blob of molten rock beneath Earth's surface. As the magma body cools, in the left-hand diagram, it loses heat energy to the surrounding environment. And as it does so, the temperature of the magma body drops. And at a certain point, crystals, that is minerals, will spontaneously begin to form in the cooling magma. That's what the yellow shapes represent. And then if we could zoom in at the microscopic or even submicroscopic level to imagine what's actually happening during the crystallization process, here's our growing crystal in the upper right diagram represented by the yellow balls. The red stuff around the growing crystals is the magma, and then these yellow balls that are sort of floating in the magma represent atoms that haven't yet linked up into a growing crystal. So here's our growing crystal, and as the atoms migrate throughout the magma, they occasionally find vacancies into which they can migrate to grow the crystal. And generally 2 things control the ability of atoms to sort of link up into growing crystals that are already there. One is simply the size of the atom. If it's the right size to fit in a vacancy, then it may do so. And then the other thing is the electric charge on the atom. If the atom has the correct electrical charge, it's also, in many cases, able to occupy vacancies around the perimeter of the growing crystal. So it's by this process, the transfer of atoms, if you will, from the magma onto the edges of the growing crystals, it's by this process that the crystals get larger and larger and larger with time. This can only happen while there's magma left, and it can only happen as long as the magma is cooling. And so at a certain point, if the magma cools, say, over large amounts of time, thousands or tens of thousands of years, there's a long time available for Mother Nature to build big crystals. On the other hand, if this magma were to erupt at Earth's surface and become a lava, then the hot lava is in contact with the cold ground and perhaps the cold atmosphere, or even cold seawater if it's a submarine eruption. And in that case, it doesn't take long at all for all of the lava to crystallize. And instead what happens is the crystals end up being very small. How small? Either barely visible with the naked eye or microscopically small, that is not visible at all. So what I'm getting at here is that the size of the crystal in an igneous rock in some sense reflects the cooling time of the magma or the lava. And the general rule is that deep beneath Earth's surface, where you have a magma body, that magma body cools slowly, and that leads to large crystals in the rock. a coarse-grained rock. Now, by large in this case, I don't mean as big as a house. I simply mean large enough to be able to see the crystals with the naked eye, maybe no more than a millimeter or so, or perhaps up to several centimeters. On the other hand, if the magma erupts at the surface and cools rapidly, that's not much time for Mother Nature to build large crystals, and so you get many more smaller crystals that are either barely visible or not visible at all. Very important chart here that you want to learn backwards and forwards and sideways to the point that you commit it to memory. So here again we have our three textural classes. Three types of textures in igneous rocks include crystalline rocks, glassy rocks, and pyroclastic igneous rocks. We'll start with the crystalline rocks. Remember, these are rocks that are composed entirely of crystals. Two things that you need to know about the rock in order to name it and formally classify it. You need to know the origin of the rock. That is, whether the rock formed intrusively or extrusively. Intrusive rocks form from slowly cooling magma deep below Earth's surface. Extrusive rocks form from rapidly cooling magma, or especially lava, very close or actually at the Earth's surface. And then in addition to that, we need to know something about the overall composition of the rock. And the way that geoscientists sort of categorize igneous rock composition is in terms of these four descriptive terms, including felsic, intermediate, mafic, and ultramafic. We apply these terms both to igneous rocks and also to magmas. The word felsic simply implies high silica. Remember that silica includes both silicon and oxygen. And so any igneous rock that's enriched in silicon and oxygen, we would say has a high silica content, and therefore it's of felsic composition. Felsic rocks tend to be composed of light-colored minerals, that is non-ferromag silicates. And so as a rule, they're light-colored. Another way of describing that is that felsic rocks have a low color index. The color index just refers to the percentage of dark-colored minerals. So felsic rocks are light-colored because they have a low color index. Intermediate rocks have a moderate or a medium silica content, and they're also medium-colored. Mafic igneous rocks have a low silica content, and they're dark-colored. Finally, ultramafic rocks, which we don't see very often in the Earth's crust, tend to be very low in terms of their silica content, and they tend to have color indices approaching 100%. Okay, so on to glassy rocks. Two main types of glassy rocks that we're going to look at in this class, including obsidian and pumice. They're both glassy rocks, but the difference is that whereas obsidian is a more or less solid mass of glass without many vesicles. Vesicles, by the way, are frozen gas escape bubbles that form on the rock as it's cooling. Pumice, on the other hand, you can think of as just highly vesicular obsidian. We'll see some pictures of this in a minute, but imagine that pumice is just obsidian with a lot of holes in it. The holes are produced as gas bubbles escape from the magma as it's cooling and are essentially frozen in place. And then finally, pyroclastic rocks. The two main pyroclastic rocks that we're going to worry about in this class include tuff and volcanic breccia. If the explosively ejected volcanic fragments are really tiny, on the order of a millimeter or two or less than that, then this produces a fine-grained rock called tuff. On the other hand, if the explosively ejected volcanic fragments that we call pyroclasts, if they're larger, on the order of maybe a few centimeters up to as large as you want just about, and all of that material gets jumbled together and becomes hardened into a rock, we call that volcanic breccia. So bottom line, you do need to become very familiar with this chart in terms of how we name and classify igneous rocks. And you also, at a descriptive level, want to become familiar with the 11 rocks on this slide. So this just reiterates something that we saw on the last slide, and also adds a little bit more information about the compositional component of igneous rocks. Again, rocks of felsic composition are enriched in silica, that is silicon and oxygen, but as a rule, felsic rocks also tend to be enriched in both potassium and sodium. They tend to be low, that is depleted in iron and magnesium and usually calcium as well. Because, as we said before, felsic rocks are light colored, they have a low color index. That just means that they have a low percentage of dark colored minerals. Intermediate rocks are sort of in between felsic rocks. Intermediate rocks are darker than felsic rocks, but lighter than mafic rocks. And in terms of their silica content, same thing. Intermediate rocks have a lower silica content than felsic rocks, but a higher silica content than mafic or ultramafic rocks. So the main column here you want to be familiar with would be silica, but to a lesser extent, you want to be familiar with these other chemical trends as well. Here's an example of what granite looks like. Granite is an example of a felsic intrusive crystalline igneous rock. And in this hand sample, each of the different color splotches represents a different crystal, a different mineral. And then this is what a true granite looks like in outcrop. This is a photograph from Joshua Tree. And you can see in the hand sample that each of the crystals is clearly visible with the naked eye. That's how you know this is an intrusive rock. That's how you know it cooled slowly, because of the large visible crystals. Here's what granite looks like up close. The sort of gray, glassy mineral is quartz. The more opaque, whitish mineral is feldspar. And then these dark flakes are biotite mica in this case. Geoscientists often use a special kind of microscope to look at rocks, what's known as a polarizing microscope. And we won't go into the details of all that, but I will just point out that generally minerals in igneous rocks are a lot easier to identify under a polarizing microscope than even in hand specimen. And what's being done here is when a geologist collects, say, a hand sample of igneous rock in the field, they bring it back to the laboratory and they use a rock saw to cut a slab of rock, maybe that thick, and they glue it to a microscope slide. And then either by hand or using machinery, that slab of rock that's now glued to the microscope slide is sanded down. It's cut down to a thickness of only 30 microns, 30 millionths of a meter thick. And at that point, most minerals in the rock are transparent. You can shine light through them, and so you can assess their optical properties in what's called a polarizing microscope. So this slide is just to illustrate some of the different common minerals in granite and sort of what they look like under a polarizing microscope. Quartz tends to be sort of cream colored to gray, sometimes a little bit yellow. Biotite ranges from black to sort of brownish, and often biotite has this sort of stipple pattern, and then this sort of basket weave pattern down at the bottom, this large crystal here, this one here, and even up in the upper right corner of the slide. This is a type of feldspar. It actually happens to be potassium feldspar. This is what rhyolite looks like in both hand specimen and outcrop. So here's a scale bar. You can see that rhyolite is a very fine-grained rock, meaning you can't really see the crystals very well with your naked eye. It also has kind of a more even color. And so right away, the fine-grained nature of rhyolite tells us two things. It cooled rapidly at or very near the Earth's surface. And the sort of volcanic landforms that are composed of rhyolite are like this. This is a photograph of what's known as a volcanic dome. Rhyolitic lava, or felsic lava, another way of saying that same thing, tends to be really, really thick, like peanut butter or toothpaste. And so when it erupts at the Earth's surface, it doesn't tend to ooze out over the landscape for large distances. Instead, it just sort of pushes upward, and the rhyolitic dome cools in place like a piston. And then also, even though we can't see the crystals in this case, I think you would agree that the shading or the overall hue of this rock is generally light colored. So that's actually how we know at a glance that this rock is silica enriched. It's felsic in composition. We know that because it's light colored. And diorite. Diorite, as you may recall, is intermediate in composition. That just means its silica content, its silicon and oxygen content, is a little bit lower than felsic rocks, but a little bit higher than mafic rocks. This is very typical of what diorite looks like in hand specimen. It contains a roughly equal mix of light colored and dark colored silicates.